it is very difficult for anyone to describe what space would be and to treat it as a separate physical dimension. If space occupied the x-axis of the abscissa of a two-dimensional graph, time, which would form the other part of the space-time continuum, would occupy the ordinate axis, identified as y. Despite appearing as a one-dimensional line on the x-axis, space would have width and length. As noted, the depth would be dictated by time, then fixed on the ordinate axis. When it comes to real space, the one that separates us from distant stars, our mind creates analogies for its behavior. That's how our memory works. Material things need to have a symbolic representation, which is normally expressed in the images we store in our brain. It's as if this brain creates a mirror image of everything outside it. Only after that could we interact with the universe, which would involve delay in translating the information. These images would form the collection of our memory. When we are distracted, we move through the images of objects as if we were perceiving them in real time. For astronomers, space would behave like an elastic band. This analogy, although incomplete, serves the interests of those who propose to describe a universe that would be in continuous expansion. The elastic band of space, in this case, would always be stretching and never contracting. Thanks to Doppler and its redshift, space is believed to be continuously stretching, pushing galaxies away from each other and gradually leading us into a dark future. This rubber band analogy, similar to the one used to tie money, provides only two conditions for space. Or it would be at rest, a situation equivalent to an unstretched rubber band, or it would be being stretched eternally, as in the case of expanding space. In this analogy of the elastic band, one could not count on a third situation in which space could be contracting. A rubber band can relax once it is stretched, but not contract like a spring. This seemingly innocuous problem shows that our assessment of space isn't complete. The most suitable model would be to imagine space as being a spring attached to a fixed end. A block is attached to the free end of the spring. Let's say that this block would be, for example, a galaxy. At the fixed end would be the observer on Earth. As the set is a symbolic representation of the harmonic behavior of light, it is understood the role of the observer, who will translate the information that light carries. The stars will only be seen if their light has already reached us. If the universe were continually expanding, the block, like the galaxy it represents, would constantly move away from the fixed end and also from its resting position. The space spring would be stretched, and the resulting force would do negative work on the galaxy, pointing in the opposite direction to the stretch. That is, as long as the total mass of the galaxy stretches space, or space stretches without depending on the direct influence of its mass, the force would point towards Earth, which would be occupying the fixed end. The mass spring analogy is far superior to the rubber band analogy, as it predicts that space could also contract. That is, the block galaxy could also approach Earth, placed at the fixed end. Note that we would be, in this case, extrapolating the behavior of light to space, as if they formed a single thing. In fact, there is no other way to evaluate space other than using cosmic radiation. Let's stick to the case of the solar system. Contrary to what would happen in the expansionary phase of the space spring, which would connect us to the Sun, in its contraction phase, the work exerted would be positive, with the resultant force pointing to the block's rest position. That is, it would no longer point to the Earth, and would instead point to the position of the Sun. This phase would correspond to the solitary action of gravity, being accompanied by acceleration of movement, and with a continuous drop in elastic potential energy. In the case of spring expansion, this would result in the deceleration of the block's movement. A gravitational tug would appear as a secondary response to the stretching of space. The secondary nature of gravity would be linked, therefore, to the behavior of the space-time continuum, which predicts that if space were to expand continuously, there would be a complementary contraction of time. This contraction would result in the transient retention of sunlight and the information it carries, because, without time, motion cannot be measured. The placement accords with the concept of a future light cone, as this cone appears to retain our star's light for 8 minutes. The negative nature of the stretching of space, capable of retaining information, allows us to suppose that the curvature of space would also be assuming a negative nature. To solve the problem of this retention of information, it would be necessary to have an inversion in the direction of the arrow of time. Space would need to stop stretching and start its centripetal relaxation, so that time could expand towards our event horizon, allowing its measurement. The inversion of the arrow of time should be accompanied by acceleration and the approach of the planet, as the force would begin to point towards the Sun and towards the rest position of space. The problem with the behavior of space is that it appears to be a phantom entity which would not have the power to communicate anything to us, at least directly. This becomes evident in the hypothesis cited by Stephen Hawking in his book, A Brief History of Time, about the death of the Sun. If the space had the power to communicate the event to us directly, we wouldn't have to wait 8 minutes. This imaginary time, predicted for the displacement of light within the future light cone of our star, would characterize a rupture in the space-time continuum, which is not officially recognized by science. The impression remains that space would be curving negatively in our future due to the transitory retention of information. As the future has not yet happened, this virtual dissociation between light and space does not exist for our memory because it cannot be measured directly. This is understandable because, being outside the future light cone of the Sun until the manifestation of its hypothetical death, the Earth would be moving towards the future point where the apocalypse would be waiting. It was at that moment that I realized that we would not be at the mercy of the space to access the information, but of its messenger. This messenger, so cherished by science, would be light and cosmic radiation as a whole. So, when we compare the behavior of space with that of a spring, we are actually merging the behavior of space with that of light itself. This would be a source of numerous interpretive problems, as we shall see later. An indication of the fusion between the behavior of light and that of space is the finding that the mass-spring analogy describes simple harmonic movement, performed only by light, and not by space. So, let's cite some examples of data obtained with the help of light. (1) The measurement of the curvature of space. Space curves because light curves, not the other way around. What allows us to indirectly suppose the existence of a black hole is the light that would be deflected by its mass and the effects of its gravity. It seems evident that it would not be space that would allow you to see the stars, as they did in the past. This was due to the light that had previously departed from their positions. The images of the stars, which you see with delay in the celestial vault at night, are part of an illusion related to your memory. They are images displaced in time. This would be a problem of our perception, and not of the universe. The stars and planets are still around, going about their existence without giving the slightest importance to what we think about them. The illusion, which allows us to look only to our past, and not to the future, would be related to the uncertainty of the position or speed of light sources. Whether at the level of atoms or the astronomical scale, we rely on the same kind of remote tracking of light. That is, in order to be seen, the particles must first be illuminated.